Section 3.3 actually has two different topics that we're going to be discussing, and one of them is rates of change. The other is behavior of graphs. So first of all, for the idea of rate of change, average rate of change you should be familiar with, and I'm expressing it in several different ways. The first I mentioned is the change in output over the change, left off an E, change in input. You can think of that as, you may have heard it mentioned as delta y. This Greek letter delta would represent a change in y over delta x. You might recognize the slope formula from algebra, y2 minus y1 over x2 minus x1. Or writing that same thing in function notation, instead of a y2 we would say f of x2, and instead of a y1 we would have f of x1 over x2 minus x1. You also might think of this as rise over run is another one that you may have heard of. So regardless of what you think of any of these terminologies, we're talking about the slope. So you're familiar with that, average rate of change, also as the slope, and all these different formulas that we can use to describe the rate of change. So here's some actual data that I looked up about the average costs for 1 gallon of gasoline in the United States, and this is over the last several years. So we can actually consider cost a function of the year. So what I want to look at here is find the average rate of change between the years 2010 and 2011. So I'd find the year 2011 and the cost of gasoline. Now remember that my function value is the C of y, the cost, so that's going to go in the numerator. So we're looking at, when we want to find the average rate of change, we want to find the change in the cost based on the year over the change in the year. So here we're going to take the different costs. So we have $3.52 was 2011 minus $2.78. And the change in years, because we're going from 2011 minus 2010, so it's just 1 year. So we're going to subtract this. $3.52 minus $2.78 gives us 74 cents over that 1 year. So the average rate of change would be 74 cents per year. For the next one I have here, find the average rate of change between the years 2015 and 2016. So I'm going to look at 2016, and I see that that was $2.14, and 2015 was $2.43. And again, my years, it's just a 1 year difference, but just to make sure that we don't mess up on a coming up problem, let's make sure we do that right. So if you take $2.14 minus $2.43, we get a negative 29 cents per year. So we have, my next question, explain the change in sign. So notice I got a positive answer here, and I got a negative answer here, and sometimes our slope is positive, sometimes our slope is negative. Well, in part A, notice that we had a price increase. So this was a price increase, which led to a positive rate of change. Here we had a price decrease, which led to a negative rate of change. And so you'd want to make sure you put units. So we had 29 cents per year would be our units, that it was decreasing. Here it was increasing at 74 cents per year. Okay, so now let's find the average rate of change over this whole period, so from 2010 to 2017. So we're going to, can't see my numbers anymore. So we're going to take 2017, we had $2.42. And in 2010, we had $2.78. And we're going to take 2017 minus 2010. And if you subtract 242 minus 278, we get negative 0.36. But this time, notice that we're dividing by 7. So if we calculate that, I get approximately negative 0.05, and the next number would be a 1. Since I'm dealing with money, I'm going to say, as a matter of fact, I'm going to write this a little better, that we have it on average, we see a 5-cent per year decrease from 2010 to 2017. Now, that's not extremely revealing of all the different price fluctuations, because if you look back at that data, you can see that there were a lot of fluctuations in between there. We see some pretty large jumps here. So then that leads me to my next question. Between what 2 consecutive years do we find the greatest rate of change? So you'll notice a couple jumps. We have a jump between 2010 and 2011. We already calculated that one, was a 74-cent increase in that 1 year. But if you notice another jump between 2014 and 2015, we see a decrease. So let's calculate that one. If we take 243 minus 336, and we know it's just a 1-year change because I said consecutive years. So if you do this one, you're going to see a difference of 93 cents. So there was actually a 93-cent decrease between those 2 consecutive years. Now, even though I said the greatest rate of change, it could be a positive or it could be a negative. We see the greatest difference. Remember, a rate of change is a difference. So between 2014 and 2015 is when we see that greatest change, the rate of change. Okay, what do you do if you have a graph and you need to estimate the average rate of change? In this case, from x equals 0 to x equals 2. So let's call this graph f of x. So if I want to estimate the rate of change, I need to know f of 2 minus f of 0 over 2 minus 0. So you're going to look over here on the graph and find the 2 and see what the height is. It looks like it's about 5. So you can kind of follow over from here. So it looks like we have a 5 minus f of 0 we can see is negative 3 over 2 minus 0. So we change this to adding the opposite. We get 8 over 2, which is 4. So my average rate of change from x equals 0 to x equals 2 is 4. Now I'm asked to estimate the average rate of change from x equals 2 to x equals 3. So we're going to take f of 3 minus f of 2 over 3 minus 2. So you look on your graph, f of 3, we're going to kind of estimate what we think that might be. It appears to be about negative 3. And f of 2 we already figured out was 5. 3 minus 2 is 1. So we get negative 8 over 1, or negative 8. So we have an average rate of change of negative 8, whereas the first one we had an average rate of change of 4. Now, one thing I do want to point out to you, remember from algebra, that when we see the greater the value, the steeper the rate of change, the steeper the slope. So we can see this rate of change here. If you compare the steepness compared to the steepness here, that makes sense that because this second portion seemed to be a little steeper. The other thing I want to point out to you is do not confuse this with the slope of a line, because you can see clearly this is curved. So this is the average rate of change. It's not linear though, because it's curved. So just watch out for that. The next idea here is behavior, the behavior of the graphs. So the first thing I want to talk about is increasing and decreasing intervals. And I want to stress and point out that these intervals are always given in terms of the domain. So we're always going to be talking about the domain, or in most cases, the values of x. So we find that a function is considered to be increasing if the graph rises as x increases. So as x moves to the right, f of x increases. As x increases, f of x increases. That tells you that the function is rising, or the function is increasing. So we can see, and one thing, imagine if you were on the function, like suppose you were a little bug crawling along the function. Well, you can see that here you would be crawling down in a downward direction. So clearly you are not increasing in height. But right here, all of a sudden, you'll notice that it's increasing. So along this portion here, along this portion here, we are increasing. Now, we're always reporting increasing intervals in terms of the values of x. So think about where we started. We started right here at 0, and we are stopping at about 2. So from x equals 0 to x equals 2, our interval is increasing. Now, if you look everywhere else, it does not appear to be increasing anywhere else. So now we're going to look at where our function is decreasing. Well, remember the little bug. As we move, as x gets larger, here the graph is falling. So it's decreasing from wherever we go all the way out here, and that continues. It was decreasing until we get to this 0, and then it changed. So how do we write that? Because my graph is not showing, and I should have put arrows right here because I did intend for that to keep going. So when we write this, it's actually decreasing from negative infinity up until 0. Because notice it's decreasing, okay? And then it changed to increasing. And then once we got to x equals 2, it changed to decreasing again, because you can kind of follow along here. And it's decreasing, and it continues to decrease as x gets larger. So we're going to use the union symbol. Then from 2 to infinity, it continues to decrease. So it's decreasing from negative infinity to 0. Then it switched to increasing from 0 to 2. And then it switched back to decreasing from 2 to infinity. I want to stress again that it's all about x. When you are writing out your increasing and decreasing intervals, it's always going to be about the domain values, so you want to make sure that you are aware of that. So what will happen in between where we were decreasing and then we switched to increasing? Well, something happens right here at that switch, and you'll notice that that appears to be a minimum value. So when we went from decreasing to increasing, we had a minimum value here. And then you'll notice right here, it appears that we have a maximum value. So we have a minimum height and a maximum height at our function. So we have some different terminologies that we use for that. Overall, they're called extreme values, or down here in red, I said they're extrema. Extrema is plural, and that can refer to either maximums or minimums. If you're just talking about one, the singular word for that is extremum. And sometimes you'll have what are either called local or relative maximum or minimum, and you can also have global or absolute. And I'm going to make sure you understand the difference. So for this maximum value that I have listed here, this is considered a local, or sometimes some books will refer to this as relative max, but not an absolute max. And here's the reason why, even though I left off my arrows again. This function continues to go up. There is no absolute maximum height of this function. But this is important because this is called a local or relative max, because relative to the points around it, it's a maximum. If I go and look at this point right here, it's a little lower, and this point's a little lower. But this is the maximum value relative to the points around it. So it's considered a relative max, also called a local max. Down here, this value that I have this arrow drawn to is a local or relative minimum. Because notice this function continues to decrease in value and height, so there is no absolute or global, that's another word for absolute minimum, but there is a relative minimum. Relative to the points around it, it is a minimum. Now when you report, if you were just asked what is the maximum or the relative max, you report the y value actually for this because you're talking about the maximum height. So we have a local max of 5 at x equals 2. So sometimes we'll report the domain value where that local max is located, but it's really a maximum of 5. That is a local max. It occurs when x equals 2. We have a local or relative minimum of -3 at x equals 0. And sometimes people will just say we have a local max and they'll list it as an ordered pair, 2, 5, and that's okay, but you wouldn't just say we have a local max of 2. It's at 2, but that's not what the maximum value is. So you want to be careful. Remember, intervals, listing increasing or decreasing intervals, you are always listing about the domain values. Listing where you have a max or a min. If you're asked the maximum value of the function, you're talking about the y value. So our toolkit functions, you might want to get this paper out. And let's talk about where these functions are increasing and decreasing. And I'm just going to write them right on here. Notice that this constant function is neither increasing or decreasing because it's a constant. If we look at our identity function, we can see that it is increasing. And if I gave the interval where it was increasing, it would be from -infinity to infinity because this particular, or the identity line, is increasing. If we look at our absolute value function, it is decreasing on -infinity to 0 because it's falling in height as x is getting larger. And then as x continues to get larger, it's increasing on the interval 0 to infinity. And notice that we have, this is going to be an absolute minimum. And the reason I can say absolute is there is no other point on my graph that goes lower than this. It is an absolute minimum. It's also a local minimum because relative to the points around it, it's a minimum. So it's both. Notice there is no maximum because I have the arrows both pointing up. There's no relative max. There's no maximum at all. For our quadratic function, it is decreasing on -infinity to 0. And I'm assuming it doesn't end there because we're talking about the whole function. And it's increasing on 0 to infinity. And we have an absolute minimum. And you could say at 0, 0. I mean, that would be allowed to say it that way. You just don't want to just report the x value. For our cubic function, notice that it is increasing always. So I'm going to say from negative infinity to infinity. This one actually has something special in here. And we talk about this maybe in this course, I'm not sure, but I know we do in calculus, where it's concave down here like a frown, and then it switches to concave up like a cup. So this actually is called a point of inflection, where it changes concavity. So that's just a bonus for today. There is no max and no min. Our reciprocal function, 1 over x. Now remember, if you're that little bug and as x gets larger and you're crawling along here, notice that it's falling. So it is decreasing from negative infinity to 0, okay, because we have a vertical asymptote at 0. And then you're the little bug and you're still crawling and you're still decreasing. So I'm going to put union 0 to infinity. Okay, now I can't just pass over that 0 because it's undefined there, so I have to write it out like this. And it is exactly the same for the next one, so I'm just going to cheat and do that because we can see, oh wait, okay, let me take that back. That's an oops, a big oops. Okay, little bug, you are crawling and you are increasing for this portion. So it is increasing from negative infinity to 0. And then you're decreasing, if you're that little bug, on the interval 0 to infinity. Our square root function is increasing on the interval from 0 to infinity. You can see that it's just increasing. And our cube root function also is increasing. This one is strictly increasing on the entire interval. Okay, so now let's talk about finding extreme values using a graphing calculator and also identifying intervals on which the function is increasing or decreasing. So you might want to pause the video and take a minute to put this in your calculator so you can make sure that you understand how to do this. I already have it in there, so I'm just going to kind of pull this over so I can use that. Okay, so I've already actually typed it in, so I typed the function in. I set my window from -5 to 5 on both axes just so that I can get a little better picture of that to see what was happening. So I want to identify the mins and maxes, and I can see them on here. Now what I don't want you to do is use trace. If you use trace, and why nothing is happening, I don't know. Okay, let's hope this works now. So I hit trace, and if you kind of bounce along here and you'll see some values, but the calculator is not extremely accurate when you do that. So what you really want to do is to go second, calc, and I'm going to go ahead and find the local minimum first. So from there, it will ask you this question to do a left bound. You can just type the left arrow until you are on the left side of the minimum, hit enter, and then hit the right arrow till you're on the right side of the minimum, hit enter, and then it will ask you to guess. Well, just go back over by where the minimum is and hit enter. And so then it will tell you approximately what that minimum value is. And you can see right here, now this is where it occurs, but using this, let me make sure this stays up in the front, I could say that I have a local min or minimum of -1.125, and it's located at x is approximately negative 1.118. Okay, so here's my minimum value, my local min. Then I can come back over here and do second calc max. You'll see we're the number 4. And it will ask me for a left bound. Now, instead of doing the arrows, you can actually use numbers. So if I typed in a negative 1 for my left bound, enter, and then I'm going to type in a 1 for my right bound, and then I'm going to type in 0 for my guess because it looks like that's where it is. And I get a maximum value, and so this one is clearly more exact there. So I have a local max of 2 at x equals 0. And then I can also find the other minimum value. Not like that though. So we have second calc min is number 3. So my left bound and my right bound, I'm going to go to the other side, and then in between. So we can see that we have some symmetry going on this one. So we have another local min at 1.118, comma, negative 1.125. Okay, so we have 2 local mins and a local max. So now what do we do when we talk about increasing and decreasing? So remember, it's decreasing where it's falling, it's increasing in between. So I can see that it's decreasing from negative infinity up until the x value that I had a minimum. Well, where was that? That was right here at negative 1.118. And then it went to increasing, and then it decreased again, so I'm going to use union, from 0, because remember it's the x value, till this minimum value, whatever the x was, which was 1.118 approximately. So that's my decreasing. And my increasing interval, so notice how I'm using my maximums and my minimums to help me find those values, but I needed the x value, not the y value, from the mins and maxes. So then it's increasing from this x value, which was negative 1.118, and it was increasing up until 0. And then it was increasing again from this x value, which was 1.118, and it increases indefinitely after that. So that would be my increasing interval. So that's how you do those. Let me put this away now. Okay, last example. This won't be long, I promise. Find the average rate of change of this function on the given interval, and it's a closed interval. It's a closed interval since the endpoints are included. So remember average rate of change? So it's the slope. So we're gonna find f of x plus h minus f of x all over x plus h minus x. So I'm just using our formula. I'm using this, f of x2 minus f of x1 over x2 minus x1. Now, that means we plug this x plus h. This gets plugged in here. So we're going to have 2, replace the x with an x plus h, quantity squared, still plus 1, minus f of x. And so I'm going to recopy this. You're going to need to use parentheses there. All over x plus h minus x. So now it's just a little bit of algebra, and we've done these before because we did some of these the other day. So we have 2, and when you multiply this out or expand it, you get x squared plus 2xh plus h squared, and then plus a 1. Distribute the minus sign. And I'm going to simplify the denominator because notice the x's cancel and just leaves an h. So I have distribute 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 2 all over h. Look for things that can cancel. So I have a 2x squared and a minus 2x squared. And that looks like all that can cancel. Okay, I caught a mistake. Sorry, because I'm trying to rush and finish this for you. You probably saw this. When I distributed, I don't know why I put a 2 there, but it should have been a 1. The reason why I caught that is because I knew that these needed to cancel. So, because it always works that way. So now we have 4xh plus 2h squared over h. I can factor out an h. And cancel. So I end up with 4x plus 2h. I know that was, you can always rewatch that if you need to. Sorry it's so long today.